It's always a good practice to open abacus in administrator mode. Right click on the abacus page and choose run as administrator. Only then abacus will be able to analyze your job after the end of the experiment. So when you open, you have to use the standard plus expression model using the default option. Now in this experiment, we will be analyzing the stress and deflection induced in a truss. What is a truss? Actually, we have seen this type of structures in bridges, in railway station staircases, in many other places where a number of beams are joined together to form some sort of a structure like this. We can also see this in the roofings of laboratories. What is a truss? A truss is a structure formed by assemblage of beams joined together by means of a weld or rivet. So, as you can see in this animation, the bridge is supported by this truss, and the truss bends and deflects, supporting the load taken up by the bridge. Okay. So, what is the need to form a truss? A single beam. You can see this truss is made up of a combination of beams. They are joined together. Either in some places they are welded, in some places they are joined by rivets or fasteners. Okay. So why do we need a truss actually? A single beam can take up some load. If I want to take up more load, a very huge load, a single beam is not possible to take up a huge load. So I am going to form some sort of a structure like this. The load is divided among the beams. They join together and take up the entire load. So that is the main function, main requirement of designing and fabricating a truss. Okay. They take up together, they combine together, they take up more load and distribute the more load among the members of the truss. Okay. Each element or each beam in a truss is denoted as member. Okay. So now experiment number 4, the question is, determine the stress and deflection of a truss whose all members are of equal length of 100 mm when loaded as shown in the diagram. Assume suitable properties and dimensions. Here you have a truss which is supported at both ends by a hinge support and a roller support, and this is the truss structure. You have to know all members. We already seen members means the beams that constitutes a truss are known as members. All members of equal length 100 mm, which means all these beams are of length 100 mm. They are joined together in this structure to form this truss as shown in diagram, and it is loaded with 1000 Newton of load at this point and 1000 Newton of load at this point, equally loaded on both the points of the truss with 1000 Newton downward force. Assume suitable dimensions and properties. So this is our problem. We are going to draw this truss in abacus, and then we are going to apply concentrated force on the 2 points, and we are going to find out how it deforms. Now we are going to give these boundary conditions as usual. We are going to apply the load. So first of all, to draw this in abacus, our first primary aim is to find out this point. Find out this point in a graph sheet, like in x-axis, y-axis. Okay, right. So since all the members are of 100 mm, okay, so this obviously means this triangle. You just consider this triangle alone. This triangle, if all the sides are equal, then we form an equilateral triangle. You know what's an equilateral triangle? All sides are equal. So angle of an equilateral triangle is 60 degree, 60 degree, 60 degree, right? So this forms an equilateral triangle. So now let us see how to find out the height of this point. I know this is 0, 0, and this point is going to be 100, 0. The beam length is 100 mm, and this point is going to be 200, 0. This is easy to plot in abacus sketcher. But how to find out this point? What is the xy coordinate of this point? I have to find out that first. Let us consider that triangle alone. I am just naming it as ABC for our convenience. So all the 3 sides are 100 mm. Now I draw a perpendicular from B to AC. This forms D. So now since this is an equilateral triangle, this perpendicular can also act as a median. It is going to split the base into two equal dimensions 50-50, right? So now by applying Pythagoras theorem to BDC, I am going to apply Pythagoras theorem to triangle BDC. So we know Pythagoras theorem, hypotenuse square BC square is equal to AD square plus DC square. So now I don't know, I want to find out BD. I'm sorry, BC square is equal to BD square plus DC square. I want to find out BD. So I'm going to bring BD this side. So BD square is equal to BC square minus DC square or CD square, whatever it is. It's going to be 100 minus 50, 100 square minus 50 square, which will be 10,000 minus 2,500. Now that's going to be 7,500. So to know the value, I am taking square root, which will come around 86.6666, which is nothing but 87 mm. So approximate position of B point is 87 mm from the horizontal. The height of the triangle, equilateral triangle, is about 87 mm. We are going to use this data abacus to compute and to draw this truss. We will see that when we go to the abacus interface, how to construct this truss. So now we move to abacus and we start drawing this truss. As usual, we begin by choosing create part, 2D planar, deformable wire. In this experiment, we are going to choose approximate size as 1000. So far, we have drawn with 200 for simple beams. So now we are going to create a truss, a network of beam structure. So we are going to choose approximate size as 1000. Click continue. So now you will be entering the sketcher. In sketcher module, first select points, create isolated point. So now you are going to define points so that they will form the truss basic structure. So the first point is 0, 0, and the next point is going to be 50, 87, and the next point will be 100, 0. You can observe the points being generated in the sketcher, and the next point is going to be 150, 87, and the next point is, and the last point this is 200, 0. So how we are giving these points? We know our truss is made up of 100 mm span and it is an equilateral triangle. So it is going to be a 100 mm equilateral triangle. So we are going to find out the height from the trigonometric ratio. It is going to be around 86.6, which is 87 roughly. And from this we are going to formulate two equilateral triangles to form the truss. Now you click create lines connected and simply connect these lines to form the basic truss shape. Once again, since we have to connect these two, this cannot be done continuously. So once again, I am connecting these 2 points. So this truss you have sketched. Now we are going to give done to exit the sketcher module. So now truss is created. So each side of the truss is going to be 100 mm and this is going to be two equilateral triangles connected together. This is your basic truss structure. So next we move to property module. In property module we are going to define the same properties. First will be density 7.9 e power minus 6 and then mechanical elasticity, elastic. So Young's modulus is 2e5. Poisson ratio is going to be 0.3. Click OK. Next we are going to create profile. The next step we are going to create profile. Now I am giving circular profile. You can also give rectangular profile and give 50-10. You can check that. So now I assume my truss is made up of circular beam. So I give circular profile, click continue, and the radius is going to be 5. And the next is create section icon. Click create section icon, beam. The same which you have done for all the experiments. Click continue. In the next edit beam section, you just give OK. Next, assign section. So once we create the section with the material attributes, we are going to assign the section. So we are going to draw a rectangle around the entire truss. You are going to select. Make sure every beam is selected. Then click done. Section assignment, edit section assignment dialog box appears. Just click OK. Then again click done. So now we have assigned the section with a circular profile and the corresponding material properties. It is a beam and we have assigned that to our diagram. Next, beam orientation. This is very important step. Once again you are selecting, clicking done and press enter. Default orientation of the truss. This is how orientation of the truss is given. The default orientation is fine. Just give enter, click OK, give done. So you have completed the property module. Next we move to assembly module. So in assembly module, once again we are going to give instance part icon. Make sure dependent mesh is selected, mesh on part, click OK. Next we move to step module and we are going to create a single step. Once again this is a single step loading, initial, static, general. Click continue. In the next, click OK. And then we choose load module. In load module, we are going to first give boundary condition. So I am going to click create boundary condition icon. I have told you earlier, the first thing you have to ensure is boundary condition step is initial. Then first, on the left side, we are going to encaster the truss. So select the point in the origin, click done. Select this point, click done. Then choose the last option, encaster. This is going to arrest all degrees of freedom for this leftmost end of the truss. Click OK. Once again, we are going to assign another boundary condition. As per our question, the right end of the truss is going to be roller support. So we choose displacement, rotation and step as initial. Click continue. Choose the rightmost end of the truss. Click done. The next dialog box that appears, you tick U2, UR3. A roller support allows movement in X direction. It arrests movement in Y direction and Z direction rotation. So this is why we are choosing. We are locking U2 and UR3. Click OK. Now you can observe these arrows appearing on the left and right side, which means you have given supports to the truss. Now we are going to apply load. So as per our question, there will be 2 point loads in these 2 points, each of magnitude 1000 Newton acting in the downward direction. So that's what we are going to give. So click on the create load icon and change the step to step 1. And the load is mechanical concentrated force point load. Click continue and click this point, first point. Click done. In the edit load dialog box appears. Once again I am reminding you, CF1 is for horizontal load, x-axis load, and CF2 is for vertical load, y-axis load. Now our load is going to be vertical. So I am giving negative sign to indicate downward direction or negative y direction. The magnitude is 1000 Newton as per the question. So I am going to give minus 1000. Click OK. You can see a small yellow arrow appearing here. Again, I am going to repeat this step and load this point on the truss. So once again, I am going to click create load. I am going to make sure step is step 1. mechanical concentrated force, click continue, select this point, click done, and once again in the edit load dialog box, as per our question, the load is minus 1000. Click OK. So we have another yellow arrow here. So now we have loaded the truss. We have given boundary condition and we have loaded the truss. Next we are going to move to mesh module. You choose mesh and first is seed part instance. Before that you choose part. You have chosen dependent on part. So we are going to choose part and then we move to seed part. So in the seed part dialog box appears, just click apply. You can notice the truss divided into small parts and click OK. Next, you are going to click mesh part icon and then click yes. So now your beam is meshed. You can see small gaps appearing. These are all nodes appearing in between. Now at last we move to job module. We are going to analyze. We move to job module and in the job manager, click the job manager. The job manager dialog box appears. Click create job dialog box. Click continue. In the next dialog box, everything is standard. So click OK. And now click on this job and click submit. Now Abacus starts analyzing the job. You can see the status of the analysis in the status here or in the status bar, command bar below here. Now analysis is being run. Abacus is now analyzing the truss. So now the analysis is completed successfully. It is available in the status. Click on results. Abacus loads the visualization module and you just click plot contours on deformed shape. So you can see that the truss is deformed in this manner. This is the deformation of the truss. And these are all the stress distributions. The red area shows the highly stressed regions and the blue area shows the least stressed regions, as you can see from the contour plot. So for deflection, we choose from this list U. So now we can see which beam members, which truss members have been deformed a lot and which truss members have been deformed less. So from this analysis, you have created or designed a truss of a typical shape. You have given material properties and loaded it with a point load in both the ends and given supports on both the extreme bases, and you have analyzed how it affects on the truss. You can do similar experiments on your own by giving pressure. You know how to give pressure instead of concentrated force. You can give pressure on the top of this entire beam and see how the truss responds. You can also give a boundary condition here, some roller support or something, and see how the truss responds. You can do a lot of experiment from this single experiment. You can try and learn. Thank you.